Hello everyone and welcome to the final lecture of General Chemistry 2. This is lecture number 21 on nuclear chemistry, and this covers OpenStack's sections 20.1 through 20.4, essentially all of chapter 20. Alright, so let's get right into it. Most chemical reactions involve either the movement of electrons and or a rearrangement of the atoms, but the nuclei of the atoms remains unchanged. In fact, one of the first things you probably learned in General Chemistry 1 is that reactions just involve the rearrangement of electrons, but they shouldn't change. However, nuclear chemistry here, we're going to see that some of these reactions do in fact involve changes to the nuclei of the atoms. So first, I want to remind you about nuclear structure and isotope notation from Gen Chem 1. So we're going to be using these symbols a lot in this unit. So the big green X here represents the chemical symbol. So this is the symbol from the periodic table. The red Z in the bottom left corner here is the atomic number, or the number of protons. And the number in the top left is the mass number, or the number of protons plus neutrons. I also want to remind you that atoms that have the same atomic number but different mass numbers are isotopes, such as these three isotopes of carbon. These can also be referred to as nucleides. So nuclei just means a certain type of nucleus. So these nucleides are often referred to by the name of the element followed by the mass number. So these we could call this carbon 12, carbon 13, and carbon 14. All right, next onto the nucleus. The nucleus is extremely small and extremely dense. So nucleons, which refers to the protons and the neutrons, which are the subatomic particles that make up the nucleus, these are held extremely close together in a nucleus. The average density of a nucleus is around 4 times 10 to the 14th grams per centimeters cubed. This is similar to taking the entire human population of the Earth and compressing that mass into a cube measuring 1 centimeter on each side. So a tremendous amount of mass in an extremely small space. Or a general fun fact that you may have seen in Gen Chem 1, if you took my Gen Chem 1 course, is that if an atom were the size of a football stadium, the nucleus would be the size of a blueberry. Alright, so since this nucleus is so small and so dense, it requires incredible amounts of energy to hold these positively charged protons, which tend to repel each other, together in such a small space. So the key force here, it's one of the 4 fundamental forces, is the strong nuclear force. This strong nuclear force is what holds the protons and neutrons together, and is stronger than the electrostatic repulsion between protons over the very short distances involved. Another term here we refer to as is the nuclear binding energy. This is the energy needed to hold the particles in a nucleus together. So let's consider the helium atom, which is made of 2 protons, 2 neutrons, and 2 electrons. The total mass of these 6 subatomic particles is 2 times 1.0073, the mass of a proton, 2 times 1.0087, this is the mass of a neutron, and remember AMU here is a unit of mass called an atomic mass unit. It's essentially just a really, really small unit of mass that's useful on this scale. And then electrons, though technically their mass is negligible, or at least we considered it to be negligible when we were initially learning about the atom, we are going to factor it in here. So there's 2 electrons with a mass of 0.00055, and we get an overall mass of 4.0331 AMU. However, when measurements of the helium atom are made, they show that the actual mass is 4.0026 AMU, which is less than the calculated mass above. So where does this mass go? Well, this difference is referred to as the mass defect. In the case of helium, this is a loss in mass of 4.0331 AMU, the expected mass, minus 4.0026 AMU, the actual mass, giving a mass defect of 0.0305 AMU. This loss in mass is due to the conversion of this mass to energy via the mass-energy equivalence, which is the equation E equals mc squared, which I'm almost certain you've heard of this equation before. This is an equation derived by Einstein, and it's a pretty famous equation as far as scientific equations go, and you're actually going to use it here. So again, this is the energy to mass conversion, or the mass energy equivalence equation. So this mass defect, this missing mass, is mass that's been converted to energy and is being used as the nuclear binding energy. So let's calculate the actual nuclear binding energy. Using the mass defect of helium, that's 0.0305 AMU, and the mass energy equivalence equation, we can calculate the nuclear binding energy. Since numerically AMU equals grams per mole, which again is something we learned about back in Gen Chem 1 in Chapter 2, if you need the review there, instead of using 0.0305 AMU, we'll instead use 0.0305 grams per mole. Now, since 1 joule is equal to a kilogram meter square over second squared, we are going to want to convert to kilograms because we're going to try and find the binding energy in joules. And when you break a joule into its base units, it's kilogram, meter squared, and second squared. So again, we're going to take that mass and we're going to convert it to kilograms. And so that mass right there is 3.05 times 10 to the negative fifth kilograms per mole. So when we work this out, E equals mc squared. The mass is 3.05 times 10 to the negative fifth kilograms per mole. C is the speed of light, 2.998 times 10 to the eighth meters per second, and that's squared. When you work this out, you should get 2.74 times 10 to the 12th. Note the units here. It's kilograms, meters squared, seconds squared, and those three units can be combined as a joule. So your answer is 2.74 times 10 to the 12th joules per mole. So the nuclear binding energy of 1 mole of helium is 2.74 times 10 to the 12th joules. And I know this, what does this number actually mean? This is actually a tremendous amount of energy. So 2.74 times 10 to the 12th joules per mole. 1 mole of helium is only 4 grams. What this means is that if you were to split 4 grams of helium, it would give off 2.74 times 10 to the 12th joules per energy. Now, for comparison, the energy released by the explosion of 1 ton of TNT is, quote, only 4.2 times 10 to the ninth joules. So 4 grams of helium would release 1,000 times as much energy as 1 ton of TNT. So with this, you can see what the motivation was behind nuclear energy and more sinister nuclear weapons. So, follow-up question then, what is the binding energy per helium nucleus? Previously, we calculated the nuclear binding energy in units of joules per mole. So if we want to keep things simple, we can use that value we used previously and convert from mole to nucleus, an individual nucleus, by simply using Avogadro's number. So taking that value, 2.74 times 10 to the 12 joules per mole, and essentially dividing by Avogadro's number, given here as 1 mole and 6.022 times 10 to the 23rd nuclei. And you would get 4.55 times 10 to the negative 12th joules per nucleus. Now, alternatively, we could have worked the initial problem by converting AMU to kilograms instead of AMU gram per mole, kilogram per mole. So remember that we initially found the binding energy as 0.0305 AMU, and this is the conversion between AMU and kilogram, and then you still just multiply by c squared, by the speed of light squared, and you would still get 4.55 times 10 to the negative 12 joules per nucleus. So you get the same answer either way. If you are asked to find just the nuclear binding energy or the binding energy of just a single nucleus, I would recommend doing this route, but oftentimes you're going to be tasked with finding the nuclear binding energy in joules per mole, and then you may be subsequently asked for a single nucleus, in which case I would use the first method. Find the energy in joules per mole, and then you can convert back to joules per nucleus using Avogadro's number. All right, so let's have you try a practice problem. The iron 2656 isotope, or we could say iron 56 isotope, has a measured atomic mass of 55.9349 AMU. First, calculate the mass defect using the information in the table. Then, calculate the binding energy in joules per mole. And then finally, calculate the binding energy in joules for a single iron nucleus. I'm not going to walk through the steps on this one, but please go ahead and pause the video and give this problem a try, and then I will reveal the answers in just a moment. Okay, correct answers here. For letter A, you should have found the answer to be 0.5302 AMU. For letter B, the answer is 4.78 times 10 to the 13th joules per mole. And for letter C, it's 7.91 times 10 to the negative 11th joule per nuclei. If you have any trouble with this problem, please go back to the example I showed with the helium nucleus. It's the same process. It's just slightly more complicated because you are dealing with 26 protons, 26 electrons, and 30 neutrons instead of the simple helium nucleus we were working with. All right, next, we're going to introduce something called the band of stability. So the nuclear binding energy is the energy required to overcome the proton-proton repulsions inside a nucleus. Larger nuclei have more protons, and they therefore have more proton-proton repulsions. So in order for such nuclei to be stable, they need more neutrons to basically space out, to push the protons away from one another. They need a larger N to Z ratio to provide enough strong forces to overcome the large number of proton-proton repulsions. So Z here, this Z axis, represents protons, and N here on, I should say the Z number on the x-axis, and this n number on the y-axis. Z represents protons, and n represents neutrons. So this straight line, or I should say this linear line right here, is the Z equals n line, where the number of protons equals the number of neutrons. And you should notice here that the band of stability, which is this dark red band in the middle here, begins to drift further and further away from the one-to-one line as the atoms or the nuclei get heavier, because again, they need more neutrons to provide enough strong forces to overcome the proton-proton repulsions. So again, the graph at the right is showing the N to Z ratio for stable nuclei, and it deviates significantly from 1 to 1, which is the solid black line, as the nuclei becomes larger. So the band of stability here, it's that sort of dark red, almost brown color, going kind of right up the middle here in like a staircase-like fashion. Nuclei which fall in the blue area of the graph, so all of these blue dots, these are unstable, and they will spontaneously decay into other nuclei that are in or closer to the band of stability, the dark areas. This area represents nuclei which do not undergo radioactive decay. A few things to note here is that nuclei with even number of protons, neutrons, or both are more likely to be stable. It's just the way the math works out. And nuclei with certain numbers of nucleons, so 2, 8, 20, 28, 50, 82, and 126, these are particularly stable. These are magic numbers which correspond to complete shells in the nucleus. And to be clear, I'm not going to expect you to remember either of these. These are just interesting facts I wanted to point out. But I am going to expect you to be able to understand and remember the general trend here, that you should remember that the band of stability begins to curve away up and to the left. It curves away up and to the left from the Z equals N line. The band of stability curves in this direction to increase that N to Z ratio to stabilize the nuclei. All right, so we're going to come back to this band of stability in a little bit more detail later in the presentation. But before we do so, we're going to go into nuclear reactions. So just as with describing other types of chemical reactions, which can involve movement and rearrangement of whole atoms, we can write an equation to describe nuclear reactions, which involve changes and rearrangements of nuclei. So just as other types of chemical reactions must be balanced, where we have the same number of atoms of each element on both sides, nuclear reactions follow similar rules. Here, though, it's a little different because the atoms will change. We're not going to balance the number of atoms. Instead, we're going to balance the mass. So the sum of the mass numbers of the reactants must equal the sum of the mass numbers of the products. We're also going to balance the charges, or more clearly, the protons, the atomic numbers. The sum of the charges, or the atomic numbers of the reactants, must equal the sum of the charges of the products. Now, when we write these reactions out, we must write them out using isotope notation. It's not just enough to use the simple atomic notation we had been using in most of this course, because again, the atoms are going to change, so we need to be able to track the mass number and what we're going to call here as the charge. Now, the reason I'm referring to this as the charge and not protons is we're going to see there are many different types of subatomic particles that may be involved in a nuclear reaction. The most common of these are going to be summarized on the next slide. 3 of these subatomic particles you already know. The proton, which can be given as 1,1p or 1,1h, so a charge of 1 and a mass of 1, and then either a little p to represent proton, or we may just use an h. The neutron, which is represented as 10n, a charge of 0 and a mass of 1, and the electron, which has a mass of 0 and a charge of -1. We will also see alpha particles. Alpha particles are high energy helium nuclei, but they do not have any electrons. So it's 4,2He, so a charge of 2 and a mass of 4. So they are essentially just these small little bundles of 2 protons and 2 neutrons, no electrons. So they can be given with the label He or with the Greek letter alpha, but it's important that it's a mass of 4 and a charge of 2. Next is a beta particle. A beta particle is essentially just a high energy electron. So it's the same as an electron, it's just higher energy. It may just use the 0, -1e notation just like an electron. It may also use the Greek letter beta. Next is a positron, which is a very interesting subatomic particle. A positron is actually a form of antimatter. It's a positively charged electron or an anti-electron. So it has the same mass, 0, but it has the opposite charge, +1. So it's literally an anti-electron. Same mass, opposite charge, and it does use a little e. So 0, +1, and e to represent a positron. And then finally, a gamma ray. Gamma rays do not have any mass or charge. This little curvy Y is the Greek letter gamma, and it's simply a very high energy burst of radiation, but it does not change the mass or the charge of the atom it's being emitted from. All right, so all of those particles are summarized here. The alpha particle, represented as 4,2He or 4,2-alpha, it's 2 protons and 2 neutrons. A beta particle, which is essentially just a high energy electron. A positron, which is a particle with the same mass as an electron but with 1 unit of positive charge. A proton, self-explanatory, a neutron, and then a gamma particle, which is just very high energy radiation. All right, so let's look at how we can balance nuclear reactions. If the mass number and charge of all but one of the particles in a nuclear reaction are known, we can identify the unknown particle by balancing the reaction. For example, if we knew that a collision of nitrogen-14 and helium-4 produced 2 products, one of which was a proton, we could identify the other product by first writing the balanced equation. 14,7n plus 4,2He forms 11p plus the unknown product. Now we know that the mass numbers must be equal on both sides. So on the left side, we have a total mass of 18, and on the right side, we have a mass of 1 plus A. Therefore, A must be equal to 17. The charges, or the atomic numbers, must be equal. We've got 7 plus 2 on the left side. This must be equal to 1 plus z on the right side. So if we've got 9 on the left, and right now just 1 on the right, z must be equal to 8. The element with the atomic number 8 is oxygen, symbol O. So the unknown product, therefore, must be 17,8O, or oxygen 17. So this is how we can balance nuclear reactions and predict the products that form. All right, so let's go ahead and have you try this problem. So please pause the video and give this problem a try, and then I'll show my work and reveal the answer in just a moment. All right, hopefully you came up with the answer of aluminum 28. Aluminum 28, so 2813Al is the correct answer here. To show the work, we've got 42He plus 2512Mg, producing a proton and an unknown element. So if we look at the mass here, we've got a mass of 29 on the left side and just a mass of 1 on the right side, meaning our unknown element must have a mass of 28. We've got a total charge of 14 on the left side and just 1 on the right side right now, meaning our unknown element must have a charge of 13. The element with Z equals 13 is Al, and the product is therefore 2813 Al. All right, let's have you try one more practice problem. The isotope 12553I, or iodine 125, combines with an electron and produces a new isotope and no other particles. Write the balanced equation for this nuclear reaction. All right, and the correct answer here is shown below. So 12553I plus 0, negative 1e, just sum these values. The mass is still 125. Note the charge actually would decrease down to 52, meaning then our new product is tellurium, Te. Next, we're going to look at radioactivity. So radioactivity is the emission of tiny energetic particles from the nuclei of certain unstable atoms. These energetic particles may be small nuclei, subatomic particles like protons, neutrons, electrons, positrons, or high-energy photons such as gamma radiation. The spontaneous change of an unstable nucleus into a different nucleus is known as radioactive decay. This unstable nucleus which decays is called the parent nucleus. The nucleus which is produced is often referred to as the daughter nucleus. The daughter nucleus may be stable or it may itself decay. So for example, if we had a parent nucleus of uranium-238, which decays via alpha particle radiation or alpha particle decay, we lose an alpha particle, the daughter nucleus would be thorium-234. So we see this alpha particle breaks off and decays, leaving thorium-234. So there are various types of radioactive decay. As previously mentioned, there is alpha decay, which is the emission of an alpha particle, a high-energy helium nucleus containing 2 protons and 2 electrons. There is beta decay. This is the emission of a beta particle, so a high-energy electron is given off. What actually occurs here is that a neutron is converted into a proton, and then an electron is given off to balance the charge. There's also gamma ray decay, or gamma radiation. Gamma rays, these are bursts of very high energy radiation which don't have any mass or charge. This is emitted when an unstable nucleus rearranges to become more stable. The atomic and mass number here do not change, only energy is released. We have positron emission, which is the emission of a positron or an anti-electron. This is actually the conversion of a proton into a neutron, with then a positron emitted to balance the charge. So these are all forms of radioactive decay. You may also see electron capture, which occurs when an electron combines with a proton and is then converted into a neutron. So to summarize these types of radioactive decay, we have alpha decay, where an alpha particle is given off. So the parent nucleus, how do you predict the daughter nucleus from the parent? You decrease the mass by 4, you decrease the charge by 2. In beta decay, to go from the parent to the daughter nucleus, again, beta decay is the conversion of a neutron into a proton. So the mass is unchanged, but the charge here actually increases by 1, going from 53 to 54. And then an electron is given off. That's the beta particle that's given off to balance the charge on both sides. See, 131 plus 0, 131, 54 plus negative 1, 53. Gamma decay, this is simply when you have an excited atom and it just gives off energy. So both the mass and the charge are unchanged. Positron emission is when a proton is converted into a neutron. So you see that the mass is unchanged, the charge actually drops by 1, and then a positron is emitted to balance the charge on both sides. And then finally, we have electron capture. Electron capture is the same end result typically as positron emission. See that the mass is unchanged and the charge decreases by 1, just the root is different. It's when an atom captures an electron, the electron combines with a proton to form a neutron, and sometimes an X-ray will be given off. All right, so let's have you practice a couple problems here. I'm going to ask you to see if you can accomplish this without me showing any problems. So please pause the video and see if you can write a balanced nuclear equation for each of the following. Alpha decay of polonium-216, and polonium is PO for reference, so you should be able to find that on the periodic table. Beta decay of actinium-228, and actinium is AC on the periodic table, and then positron emission of sodium-22, and you should know where sodium is. So please pause the video and try to answer these 3 questions. All right, let's walk through these answers. Alpha decay of polonium-216, 216-84PO. So we're giving off an alpha particle, which is 4,2He or 4,2 alpha. So what's the mass that remains? 216 minus 4 is 212. 84 minus 2 is 82. So our resulting daughter nucleus is 212-82, which is lead. Lead has a charge or a proton number, 82 protons, I should say, a Z number of 82. Next, beta decay of 228. So in beta decay, an electron is given off, so 228-89 AC on the left side, and then 0, -1 E or 0, -1 beta on the right side. So if we look, the mass is unchanged, so our daughter nucleus should still have a mass of 228. Here we should note that if we want the two sides to balance, we've got 89 on the left side, -1 on the right side. This new daughter nucleus actually needs to have a charge of 90. It has need to have 90 protons. So this makes our daughter nucleus 228-90, which refers to thorium. Thorium is number 90 on the periodic table. And finally, positron emission of sodium-22. We've got 2211 and a positron is just like an electron, but with a charge of +1. So no mass, so the charge is unchanged. So 22 here and 22 here. Note that we have a charge of 1, and so thus here the charge should be 10. So 10 plus 1 giving us 11. So our daughter nucleus is an atom of neon 22. All right, so those are the different types of radioactive decay. That's how we write out those reactions. Now let's go back to the band of stability. We're going to look at the band of stability with reference to the nuclide decay chart. So the nuclide decay chart here shows the band of stability. Here it's represented by black dots going kind of up the middle relatively. It also shows all known radioactive nuclei color-coded by their primary decay mode. There are some pretty clear patterns evident here based on whether the nuclide lies above or below the band of stability. So note the ones down here below the band of stability versus the ones up top here. The ones up top are all blue, the ones on the bottom are all pink, and then out here with the heavy atoms we typically see a lot of yellow, which refers to the alpha particles. So what do these colors specifically refer to, and what do they tell us about the types of radioactive decay that occur in an attempt to become more stable? Well, first let's talk about the easy one. Those yellow dots way out towards the right, that was alpha decay, and alpha decay decreases n by 2. It also decreases z by 2, right? It decreases the number of neutrons by 2. It decreases the number of protons by 2. This occurs mainly in heavy nuclei, typically with z values greater than 83. It does increase the n to z ratio very slightly, but not by much. This is typically just to bring these atoms back closer to the band of stability, because you'll see a lot of them are actually out past where the band of stability is. So losing 2 of each brings them closer to this band of stability right here. Next is beta decay. Beta decay converts a neutron into a proton. So this decreases n by 1 and it increases z by 1. So this is observed in nuclei with a large n to z ratio. This results in a decreased n to z ratio in the daughter nuclide. So beta decay is what happens with these up here, these blue dots. Anything that is up here is likely to undergo beta decay, because beta decay, again, it converts a neutron into a proton. So if I go back to this chart here, if I'm right here and I'm trying to get to the band of stability, I need to go this direction, right? I need to go down and to the right. How do I go down? Decrease the number of neutrons. How do I go right? Increase the number of protons. So that's why these here that have these high N to Z ratios, they are likely to undergo beta decay. They'll decrease the number of neutrons and increase the number of protons to try to get closer to this band of stability. And then finally, positron emission slash electron capture. Positron emission is more common, but both are possible. They both do the same thing. They convert a proton into a neutron. So these decrease Z by 1. They increase N by 1. These are observed in nuclei with small N to Z ratio, resulting in an increased N to Z ratio in the daughter nuclide. Let's look at this in a little more detail. Again, remember that the goal of radioactive decay is to try to get closer to the band of stability. So if we look at all these yellow dots, alpha decay, these decrease N by 2 and decrease Z by 2. So they make it easier to try and get towards that band of stability. As I was mentioning before, all these blue dots are where beta decay occurs, which converts a neutron into a proton, decreasing N by 1 and increasing Z by 1. So you move basically towards the bottom right on the figure. And then all these pink dots down here, these refer to either positron emission or electron capture, which converts a proton into a neutron, which decreases Z by 1, which moves you left on the graph, and it increases N by 1, which moves you up. And that makes sense, right? If I'm a nuclide right here, I need to go up and to the left to get to the band of stability. So I'm going to favor positron emission, which converts a proton into a neutron, which moves me left and up on the nuclei decay chart here. All right, so here's a practice question for you to try. How will the N to Z ratio of a nucleus change during each of the following types of radioactive decay? And hint, I want you to think about the number of protons and number of neutrons that will change for each. So please try these 5 questions here. How will the N to Z ratio change during each of the following types of radioactive decay? Okay, the answers here. Letter A, an alpha particle is emitted. So N goes down by 2 and Z goes down by 2. So I would accept no change as a possible answer here, since both N and Z are decreasing by 2. But in reality, this is probably a slight increase in the N over Z ratio. Letter B, this one's easy to answer. A beta particle is emitted. So when a beta particle is emitted, remember here, we are converting a neutron into a proton. So when a neutron is converted into a proton, N is going down, Z is going up. And so this N to Z ratio is definitely going to decrease if the numerator is getting smaller and the denominator is getting bigger. So decrease is the answer for letter B. Letter C, gamma radiation is emitted, no change. Remember that gamma radiation being emitted does not affect the mass or the charge numbers. D and E have the same answer, a positron being emitted or an electron being captured. These do the same thing. These convert a proton into a neutron, and so these would increase the ratio. A proton is being converted into a neutron, so Z is going down by 1, N is going up by 1. So if the denominator is getting smaller, the numerator is getting bigger, the N over Z ratio is definitely going to increase. So it's increase for D and E. I've got one more practice problem for you to try. The following nuclei do not lie in the band of stability. Based on the N over Z ratio of each, how would you expect each to decay? So remember that really big nucleides are likely to undergo alpha decay. If you have a really big N to Z ratio, you're probably undergoing beta decay. If you have a small N to Z ratio, you're likely going to undergo positron emission slash electron capture. So with that in mind, see if you can answer these 5 questions. All right, the answers here. Letter A, we should note that we have a pretty small n over z ratio here, only 13 neutrons to 15 protons. So when we have a small n over z ratio, we need to convert a proton to a neutron, which means the answer is either positron emission or electron capture for letter A. Letter B, we've got a big nucleus. Anytime your z value, your number of protons, is greater than 83, you're likely to undergo alpha decay. So both letters B and E, the answer would be alpha decay. Letter C, we again have a small n over z ratio. We have 20 protons but 17 neutrons. So this one is once again positron emission or electron capture. And then letter D, here we have a very big n over z ratio. We have 6 protons to 3 neutrons. We need to convert a neutron into a proton, and this is beta decay. So letter D, beta decay. All right, next we're going to explain how different nuclides decay at different rates. So example here would be thorium-232, a very, very stable nuclide. It has a half-life of 1.4 times 10 to the 10th, or 14 billion years. So it would take 14 billion years for half of these thorium atoms to decay. Whereas radon-220, pretty unstable, has a half-life of only 1 minute. So every 1 minute, half the radon-220 atoms would decay. It's important to note, however, that radioactive decay follows an exponential decay curve, which we can describe with first order kinetics. So we talked about this a little bit when we learned about kinetics back in Unit 2. Remember that all radioactive decay, it's always described with first order kinetics. All right, so this figure on the right here is showing the decrease in the number of thorium atoms in a sample as a function of time. So let's discuss radioactive half-lives a little further. Radioactive decay follows first-order kinetics. Each different radioactive nuclide has a characteristic half-life, which we described with the variable t 1/2. Again, recalling that half-life is the time required for half of the starting material to convert to product. The equations for first-order kinetics that we discussed earlier in the semester back in Unit 2 can be applied here as well. So these were the equations we used for first-order kinetics. It was natural log AT equals negative KT plus natural log A0, and t to the 1/2 equals ln2 over k. You may also see it represented a little bit differently, where we say natural log nt equals negative lambda t plus ln of n0. Here, we're substituting n, number of nuclei for concentration, and we're substituting lambda as decay constant for rate constant. So lambda here does not mean wavelength. I know that you used lambda for wavelength in the energy and light section of Gen Chem 1, but here lambda means decay constant, and it's just a substitute for a rate constant. So let's look at a practice problem. Cobalt-60 decays with a half-life of 5.27 years to produce nickel-60. What is the decay constant for the decay of cobalt-60? Then second, calculate what percent of a sample of cobalt-60 will remain after 15 years. And then letter C, how long will it take a sample of cobalt-60 to decay enough so that only 2% of the original sample remains? I'm not going to walk through these problems because you should know how to do these based on what we covered in Unit 2. But here's all of the equations you are going to need. So letter A, what is the decay constant? You're going to want to use this equation. And then for questions B and C, you'll want to use one of these two versions of the equations. And I also want to give you a hint that might be useful anytime you're being asked to solve like what percent remains or it involves a percentage. It's probably best to let n0, the original number of nuclides, let that equal 1 or 100%, and then nt will be the percent remaining in decimal form. So if it's like 2%, you could set n0 equal to 1, and then that would make nt 0.02. So please go ahead and pause the video and see if you can come up with the answers for letters A, B, and C. All right, and the answers are listed here. Next, we're going to talk about radiometric dating. This is the use of radioactivity to measure the age of fossils and other artifacts. So scientists can use the presence of natural radioactivity in our environment to estimate the ages of fossils and artifacts with a technique called radiometric dating. In carbon-14 dating, the ratio of carbon-14 to carbon-12 in a sample is compared with the ratio of carbon-14 to carbon-12 in the atmosphere. During photosynthesis, plants obtain carbon, all isotopes, from the atmosphere, which means that the carbon-14 to carbon-12 ratio in living plants is the same as the atmospheric carbon-14 to carbon-12 ratio. However, when an organism dies, it is no longer exchanging carbon with its environment. Carbon-12 is a stable isotope, so its concentration will not change. However, carbon-14 is a radioactive isotope, and so the organism, as the organism decays, the carbon-14 to carbon-12 ratio will start decreasing because the amount of carbon-14 it's going to slowly decay over time. So an example to show here a diagram. The carbon-14 to carbon-12 ratio is constant in living organisms, but when that organism dies and it falls into the soil, the radioactive carbon-14 is taken in by the plants and animals, and over time, after death, the carbon-14 will begin to decay, and as it decays over time, the carbon-14 to carbon-12 ratio is going to decrease. So what we can do here is we can compare the ratio in dead tissue to the ratio in living organisms, and this will actually tell us how long ago the organism lived and how long ago the organism died. So let's look at an example problem. Samples of seeds and other plant matter from King Tutankhamun's, I think that's how it's pronounced, or King Tut's tomb have a carbon-14 activity of 9.07 disintegrations per minute per gram, or DMG. How long ago were these plants alive, given an initial C14 activity of 13.6 DMG and a half-life of 5,730 years for carbon-14? All right, I'm again going to ask you to pause the video and give this problem a try, but I am going to walk through the steps on the next slide here. So let me back up. Here are the equations that you will need. Please see if you can solve this problem. I'll go ahead and pause the video, and then in just a moment I'll go through the answers on the next, or the work and the answer on the next slide. All right, so the correct answer you should have found here is about 3,350 years. How do we find this? Well, again, the question is asking how long ago, so really what we're trying to solve for here is t. Now, on a question like this, where it says a C14 activity of 9.07 disintegrations, so that's the current activity, that 9.07 can be used as your NT value. And then given an initial activity of 13.6, that can be used as your N0 value. And then the half-life is 5,730 years, which is your T1/2. So you can use first this equation to solve for the decay constant. So lambda equals ln2 over T to the 1/2. T to the 1/2 is 5,730 years, and so we can solve for lambda and find that lambda, the decay constant, is 1.2097 times 10 to the negative fourth inverse years. Then we're going to use this equation rearranged to solve for t. So t is equal to negative 1 over 1.2097 times 10 to the negative fourth inverse years, the decay constant, times the natural log of nt over n0, where nt is 9.07 and n0 is 13.6. And when I work this out, again, I get about 3,350 years. So on problems like these, you're just going to use some version, let me back up, of these equations, remembering that N0 is the initial number of nucleides or the initial activity, NT is the current number of nucleides or the current activity, lambda is the decay constant, which is just the rate constant, and T is time. All right, let's jump ahead to our last couple of topics. So first, on the synthesis of new elements. Prior to 1940, the heaviest known element was uranium, atomic number 92. Since then, many artificial elements, everything after U on the periodic table has been made via the process of nuclear transmutation using particle accelerators. One example is the synthesis of element 93, neptunium, which is formed by bombarding uranium 238 with neutrons, and eventually this leads to the formation of neptunium as well as some plutonium. Again, this creates unstable uranium-239, which can decay into neptunium-239. This is actually also radioactive and will eventually decay into plutonium. But this is an example of how Neptunium, NP, was synthesized via transmutation, which just basically means uranium-238 was placed inside a particle accelerator, and this particle accelerator accelerated neutrons, and it bombarded the uranium with neutrons, eventually forming the neptunium-239. I do want to give a little asterisk here. Plutonium was originally synthesized, plutonium number 94, but it was actually later found to be naturally occurring in nature. So technically, plutonium is the heaviest naturally occurring element found in nature, not uranium. But originally, everything beyond uranium was synthesized, and this still holds true besides plutonium. So everything past uranium besides number 94, plutonium, was synthesized. All right, and we're going to finish today by talking about first nuclear fission. Fission is the breaking of a large nucleus into smaller pieces. Fission does not occur naturally, but is induced via bombardment with neutrons. The breaking here is somewhat random, with the possible formation of a number of different products. So, for example, we could take uranium-235, bombard it with neutrons, which forms uranium-236, a very unstable nucleus, which will then break via fission into smaller nuclei and then give off a bunch of neutrons. Now, what is very helpful here is that a huge amount of energy is produced by the fission of heavy elements. For example, the fission of a single gram of uranium-235 produces about 7.66 times 10 to the 10th joules of energy, more than 1 ton of TNT. Now, these fission reactions often produce 2 or 3 neutrons, which each then can go on to initiate fusion of other nuclei, leading to a chain reaction. And these chain reactions basically can be very useful for the production of, preferably the production of energy. So anytime you see a nuclear a nuclear power plant, what's going on inside that reactor is nuclear fission, a carefully managed nuclear fission reaction, where a radioactive element is being bombarded with neutrons. It's undergoing fission, it's breaking into smaller elements. That fission gives off multiple neutrons, which can then initiate the fission reactions of multiple more elements. And again, now we get an exponential chain reaction occurring here. And the other type of reaction we can see is nuclear fusion. So when we think fission, we think fissure, we think breaking apart. Fusion, we think combining. So fusion is the process of combining light nuclei into heavier ones. The process of fusion is accompanied by the conversion of mass into a large amount of energy. It is the principal source of energy in our sun and other stars. So our sun is actually just a giant fusion reactor. It's basically hydrogen. Hydrogen nuclei are being fused together into a helium nucleus as well as a couple of positrons. The helium nucleus has a mass that's about 0.7% less than 4 hydrogen nuclei. This mass defect equates to about 3.6 times 10 to the 14th joules of energy per mole of helium produced. So the fusion process is a lot more energy efficient than the fission process, especially if we're comparing this fusion process to the fission process. So this is why there's been a lot of time and energy and money spent into trying to make nuclear fusion power a reality, because it's a lot cleaner. You don't have any radioactive byproducts, and it's significantly more efficient. It's just really hard to get these reactions going. They require intense amounts of heat and pressure. All right, and I've got one last practice problem for you. Determine whether each of the following reactions is a fission reaction or a fusion reaction. So try these two, see if you can label them as either fusion or fission. All right, you should have come up with these as your answers. Letter A is fusion, and letter B is fission. Anytime you're given a problem like this, look for the heaviest product. If the heaviest element present, I should say. If the heaviest element present is on the product side, it's fusion. If the heaviest element present is on the reactant side, it's fission. So A is fusion, B is fission. I've got 5 more practice problems for you to try, so please go ahead and pause the video and give these problems a try, and then in just a moment I will reveal the answers. All right, here are the answers to those 5 questions. That's it for this video, and that's it for this course. That is the end of General Chemistry 2. Thank you for sticking with me to the end. I hope you found these videos useful and informative. And as always, please feel free to reach out to me if you have any questions, whether it be via email or just commenting down below. I will do my best to help you. I hope you enjoyed the videos. I hope you enjoyed the course, or at least you are doing well in the course. But that's it for me. I hope you have a great day.